record. Okay. So we're implementing a fraction class from the previous slide and test it by creating several fractions and adding them together and displaying the results. Okay, yada, yada, yada. One thing I did like, I saw earlier, maybe they erased it, but I'm guessing one of the teams working on homework was in this room. So I saw you writing code. I like that. That's the stuff you got to be doing, because I realized that this stuff is not easy when you're first learning it. And I really wish there was a way for, and you're going to see it today, it's not hard. I'm going to make it look pretty easy. And I really wish there was a way for me to make it easier for you at first, but you just got to put the reps in. And I promise you, if you don't believe me now, you'll come back next year and you will believe me. It's just the thing. And like I said, I've been doing this for longer than most of you have been things. I started teaching college in 2000, still on the chalkboard, and it's been it was a thing then, it's going to be a thing today, and it's going to be a thing for a while. So trust me, but it will be worth it in the end. Okay, so let me just bring up the slide where we designed the thing. So we decided that, so we've been working with classes, right? So a fraction is going to have some private members, a numerator and denominator, probably both integers. And then it's going to have some public members. It's going to have a constructor, a way of building your fraction, and then a way of displaying it. And then we need to be able to add fractions. So this is the secret sauce for today's assignment, where you got to drill this keyword. All right. So hopefully, for those of you who got it done, in the end, through all your battling, you have a little bit better concept of what this keyword means. But we'll keep drilling that, because it is a hard concept to wrap your mind around. But let's go and write this. Okay, that is not this class. Projects. Do we already have a fraction thing?
No.
Did I give you like starting code though?
It was the same starting code that we had some class.
Oh, this class intro?
Yeah.
Okay, so we'll create a new project for it. Sound reasonable enough. And let me go ahead and save it. Sorry, we'll call this CSC200 fraction stuff. Something like that. Okay. So I'll go ahead and let's see. Last time, did I already talk about header files and we separated stuff into different files? Okay, so let me go ahead and do that in here. I'm going to really model it the way that I would say a traditional programmer would write it, even though we did talk about you could just stuff everything in one file if you wanted to. But we kind of talked about self-documenting things. So we're going to create a fraction header file, Fractionhpp. All right, so we're going to have a class called fraction. All right. Oh, there we go. And in the private section here, we're going to have an int numerator and an int denominator. Why is denominator such a hard word to spell? Yeah, it's just one of those words. And see, you can't blame me for that part though. That's just a fraction thing. They should have named it better. is what it can. All right, so then in our public section here, we'll create our We'll create our constructor for fraction, which has the same name as the class. And this guy will take in an int numerator and an int denominator. And then I said we're going to have a display method. So it'll be void display, takes no parameters, and this guy will display a fraction to the screen. All right, so let's just stop with this. All right, we'll stop with this thing. We'll go and implement our fraction, and then we'll build a couple of fractions and make sure we can display them on the screen. Start with that and make sure we have a foundation that's ready for us to write broken add code. Sound good? Okay. So I need my fraction CPP. And we will include fraction HPP here. All right, now I'm gonna just steal these two things. Paste it in here. So I'm going to be implementing these couple of things now. But I need to make sure I tell it this guy's going to belong to the fraction class. And this guy's going to belong to the fraction class. So that's what I do to link it to that header file. Header file is my documentation. This file is my implementation. This is me telling it I am now implementing this constructor for this class. All right, so our constructor for fraction, we're going to set this guy's numerator equal to the numerator that was passed in, and this guy's denominator equal to the denominator that was passed in. That is to say, somebody is going to build a fraction and they're going to hand you a numerator, they're going to hand you a denominator. And while I'm being born, if I'm that fraction, I will set my numerator, this numerator, equal to whatever that guy passed me. And I'll set this denominator equal to whatever that guy passed me. All right, that's what I'm doing here. I'm setting my numerator field equal to whatever was passed in here, my denominator field equal to whatever was passed in here. All right, so that's our constructor for this guy. Now in display, we're not returning a value, so it's void. I'm going to display something to the screen. Now we've used cout for displaying stuff, so that means I'm going to need IO stream in here. So I'm going to include IO stream and then using namespace standard. And then I'll go ahead and just do a cout this numerator. And then maybe do like a slash like that. And this denominator. And L, something like that. That's just what we'll decide a fraction looks like when it displays itself. Then we'll go into main. We'll go ahead and include fraction HPP here. I will go ahead and create a fraction pointer F1 is equal to a new fraction. We'll make this guy 1/2. Fraction pointer F2 is equal to a new fraction. I don't know what, 3/5. And then we'll ask F1 to display himself. We'll ask F2 to display himself. So there's our two fractions. Okay, so before we go any further, questions on what we've done up to this point? Go ahead.
Do we have to use multiple files?
You don't have to. But if you're not going to use multiple files, I want you to do it for a good reason. Yeah, so this is kind of, what we talked about last class is if you look at fraction, the header file for fraction, this guy gives you just kind of a snapshot of what fractions are right now. And we're about to add an add function to this guy, where this guy is the implementation of that. So even though this is pretty short, we do have some extra things in here that might distract us from seeing what a fraction is capable of at a glance. So I would say that this is probably the preferred way of doing this, even though it feels a little tedious, right?
I did one file.
You just put everything inside of main
No, I
CPP.
put main CPP and then put fraction HPP.
and then you wrote your implementation inside of that. That's fine.
Okay.
Because I think if you remember last time I mentioned that when you say include fraction HPP,
Yeah.
no weird magic is happening. What it's doing is it is literally taking the entire contents of this file and it is replacing this line with that. It's not doing any sort of weird linking thing or treating header files as this special mystery. It's just saying, oh, you gave me this line. I'm going to replace this one line with all the crap you have in that file. A human being's not going to see it, but I'll do it when I go to compile it. All right, go ahead.
How does it know to get Fractioncpp though? I'm not, unless.
This link here, because in fraction HPP, so Fractioncpp included fraction HPP, and then we actually implemented it here. There's going to be this thing called an object code that will already have fraction implemented. So it never actually goes to Fractioncpp from in here. Instead, it says, oh, there's going to be a thing called fraction. You've told me all about it. This is kind of like prototyping. You've told me this dude's going to exist. And now this is where it's actually implemented, and it's going to kind of be there at runtime. Yeah, but for a good reason. It's how compilers work. When your compiler goes through all this code, it's going to compile all these different files, and it's going to make sure that, you know, when we prototyped functions, you know, you're kind of saying, trust me, down below, I'm going to write a function called this. And I'm telling you about it now because I'm going to use it in here. So when it compiles a file, it'll make some assumptions based on what you've promised that it's going to eventually run into your implementation. Because before your code actually runs, there's a final step, a linking step, where it actually builds your executable. So with compiling, you kind of have like there's a couple of steps. One step is go through files, make sure it's legal code. And part of making sure it's legal code is making sure that it's going to check that, okay, you're using fractions in here. Did you at least tell me that they will exist? Yes. But then the last part is it's going to link all those things together, the object files that were created as an output from the compiler, the low-level code. Remember, a compiler converts from high-level code down to low-level code. It'll take all of that low-level code and link it together and create an executable for the current operating system that you're on. And that executable, that's when the actual implementation for all that stuff needs to be there. But we're basically, you know, don't call our bluff if you don't implement it, because at runtime it'll break if you don't actually write it. So I would say that this guy right here does kind of become magical. That's the thing that links the CPP file to the HPP file.
And then in main, just because we know that, hey, the fraction exists somewhere because HPP.
Yeah, when I wrote this here, that allows this to compile.
And then,
But when it goes to run, it's trusting that I actually implemented it somewhere. All right, any other questions on this so far? Okay, so now let's go right at. So fraction HPP, we're going to add a new function here. It'll be a public function because we want to be able to call it outside, right? We want to be able to add fractions to each other. And this guy's going to return a fraction. So he's going to return the address to where a fraction lives. It's going to be called add, and he's going to take a fraction pointer f as a parameter. You can call it whatever you want. I'll just call it fraction or call it f. Actually, to better understand the this keyword, I'm going to call this guy other fraction. I'm going to name him other fraction. Okay, so I prototyped it here. Now I'll go and implement it in my Fractioncpp. Okay. No scrolling. Okay. Now, in order to add fractions together, we need to have a common denominator, right? Okay, well, how do I get a common denominator? I multiply the other two denominators together. Okay, we're not reducing it yet. We'll look at that today. But so if I say int common denom is equal to, I need to access the two denominators I have access to. That will be my denominator, the denominator owned by this instance of fraction, who at whichever fractions add method we call. That's how we access his denominator. And I'm going to multiply that times the other fractions denominator. Now, this is where things maybe get a little interesting. Last time we talked about getters and setters. So inside the fraction class here, we had these guys set up as private. And our experience from last class was, well, if you have a field set up as private, you can only access it inside of the fraction class, right? So you might say, well, in order to access that denominator, don't I need to write a getter? Which class am I in right now? I'm in the fraction class. Listen to the language I'm using. In order to access these private members, you can only access them from within the fraction class. The fraction class, not that particular instance's fraction class. I can access my own denominator, or I can access other fractions denominators in here, as long as I'm currently inside the fraction class. Now, you didn't have to do this. You could have written yourself a getter, right, to get the denominator and then called it in here. Wouldn't have hurt anything, but you didn't have to. We've still protected our denominator here from the public making changes to it. But we can access it inside of Fractioncpp because it's private and we're currently in the fraction class. So we would say our context here is inside the fraction class. So I have access to all of the public and private members of the fraction class when I'm here. So there's my new common denominator. Okay, now we need to get our numerator and we need to get our new numerators to add together, right? So we're going to say int num1 is equal to this numerator times other fraction denominator. Int num2 is equal to this. Well, actually, we'll write it the same way. Other fraction numerator times this denominator. So we're cross multiplying here to get our updated numerators for each side. So we'll call this guy new numerator will be equal to num1 plus num2. We already have our common denominator. So we're going to say, we'll say fraction pointer answer is equal to a new fraction, passing it new numerator and common denominator. And then we'll return that answer.
Oh, common.
Oh, I called it common denom up here. All right, so these are just four variables. I'm just doing the math. What's my common denominator going to be? It's going to be this fraction's denominator times the other fraction's denominator. If I am the fraction whose add method is being called, this is me. So I'm going to say our common denominator is going to be my denominator multiplied whatever the other fraction's denominator that you passed in. Then we need to update our two numerators. So I'm just doing those in separate variables. So to bring our numerators in line with our common denominator, I need to change my numerator and multiply it by the other guy's denominator. For the other numerator, I need to change the other guy's numerator, multiply it by my denominator. And now I have updated num1 and num2 to be compatible numerators with my common denominator. And now I can just add them together and store the result in this variable. So I'm remembering 4 things here, just stepping me through. Go ahead. That's in here. I did do it already. This is, well, I haven't called add yet, but yeah, it would. So here in a second, I'm going to say fraction pointer F3 is equal to F1 add F2. This guy is other fraction. And this guy is this. Correct. And F1, we call him by his nickname inside here, which is this. And just to flip the tables a little bit, just to drive this point home, I'll say fraction pointer F4 is equal to F2 add F1. Now I'm calling F2's add function, which is the same function. It's just the one he owns. So his function knows about him through the keyword this. So inside of F2's add function, when you say this, you're talking about F2. And when you say other fraction, you're talking about F1. This was the parameter that was passed in. All right, so just reviewing what we did here. This is going to be our common denominator. The denominators multiplied together. Here's my updated numerator by making it compatible with the common denominator. Here's my other updated numerator, making it compatible with my common denominator. Here's my sum of the 2 numerators in my new numerator. Then I'm going to build a brand new fraction with the new numerator and my common denominator, and then I'll return that guy. (11/10) is the sum of 1/2 and 3/5. Go ahead.
So we did have to use the fraction.
What do you mean?
So in the assignment, we gave this
Okay. Oh, right here. Oh, yeah. I mean, this F here is just a variable name. So nothing, I can call this guy F in here if you want to. Nothing keeps you from calling this guy F. It is taking in a pointer. Oh, you mean what I put in words here? Oh, I mean, you should use pointers. That's what objects are. Because the only way you know how to build an object is with the new keyword. This guy right here. And what does the new keyword do? Yeah, that's our real estate agent. He always gives you a memory address. That's what you're going to get back from that guy. I mean, you could write it to take in an actual fraction. If I wanted to do that, if add happened to be written to take in a fraction instead of a fraction pointer, I would have to pass it star F2, the value that lives at that address. Yeah, so you could have made it work that way. All right. So questions on how this works. Diving back in here, that's our add function. Good. Oh, it's for any function that has a return type. When you implement it in here, you connect it to the header file by putting it next to the name of the function. It's just the syntax for how you make that connection. It's the return type's always to the left. Even up here, our return type was void. Yeah.
So for other fractions, arrow type denominator, that's because you're like
Okay, yeah, so the question is, and this is for the folks online, why do we have to use the arrow instead of a dot, right? There seems it can initially appear like we're coin flipping when you use a dot versus when you use an arrow. So I think you mostly have it right. The idea here is that let me actually do it outside here because I think it'll be cleaner. So when I say F1 display like that instead of F1 dot display, why is this correct versus this incorrect? That's the question you're asking, right? All right. And the difference is, so he just tried to describe F1. He said, well, is it because F1's effectively two integers? That's mostly true. I mean, simplified, that's mostly true. Really, what is F1? F1 is a pointer to a place in memory where two integers kind of live in some sort of package deal called a class, right? Somewhere we have this thing called a class where we've shoved a couple of integers into, and we've also taught it how to do a couple of things. We've zipped it up and we've thrown it up in memory somewhere, and now we have a pointer to that place. So the arrow tells us to not use F1. Don't treat F1 as the value. Instead, dereference F1 and actually go to the place in memory where the actual fraction lives, where that instance of the class with those two integers in it actually lives. This syntax here, if I say F1 dot display, this says whatever this guy is, call his display function. And this guy here is a memory address. That makes sense? Okay, so if I had a piece of paper that had the address to my house, and I tell this piece of paper, open the garage, that's not going to work because I'm basically telling a piece of paper to open the garage. If I go to the house and then push the button to open the garage will open, right? So that's the difference between saying, you know, this is F1. F1 open your garage versus F1. So F1 dot open garage would be if I'm talking to this guy. F1 arrow open garage would follow this guy to my actual house and then open the garage. Make sense? Go ahead. These two lines mean the same thing. Because this says, give me the value that lives at that address and then call his display method. Yeah, I think it'll make you use parentheses because it won't like the syntax of having star F1 and the dot. It won't know which of these things to do first. So by parentheses, you're specifically saying, look, go and dereference this guy and give me the fraction. Then once I have the actual fraction, call his display method. Right, and we're not using dots here. Yeah, I mean, if you notice my original thing, there's no dots. In fact, I would say it's going to be pretty rare for us to use dots with classes. Structs we would, but when we talked about structs, I kind of mentioned this was more academic. I'm never going to test you on it. Not that structs should be thrown out the window as something you're never going to see again. I just want to keep our focus on kind of eye on the prize, right? Yeah, so in our world here, arrows are pretty much everything in C++. In Java, we're going to use dots, but those dots mean the same thing as an arrow in Java because Java handles memory for us. If something's an address, it'll dereference it. If something's a value, it doesn't have to dereference it, and it just won't. In C++, we have to be the decider of what kind of animal we're dealing with. And again, that's kind of the reason why we use C++ in here is, yes, it's tedious, feels inconvenient, but forces us as beginning programmers to ask ourselves, what kind of animal am I dealing with here? So that next semester, when we use a more modern language and it does some of these things for us, you'll appreciate it. And it won't just magically work. It's like, oh, this is easier. Well, it's easier now because you understood the way it used to work. And now you kind of like the fact that you have, you know, I usually reference like, I don't know, automatic transmission versus stick shift. Stick shift is fun to drive when you first start driving, but then it's like, hey, I kind of want to be able to drink my coffee, and you know, I only want to use one hand and just let the car kind of do its thing. Or the if you want to go older school than that, the idea of fuel injected engine versus something where you have to, you know, squeeze the little pump thing to get the fuel started in there before you ignite it. So what if every single time you got into your car, what if every single time you got into the car, you had to squeeze the little bulb to get enough fuel to your engine to when you turn the key, it, you know, the explosion happens and the engine turns over. I mean, it wouldn't be the end of the world, but it would feel more tedious than getting in now. You just turn it on, right? Or you go even older school where you have to get out and actually crank the engine, kind of like with the pull start lawnmowers, you know, that type of thing. So we appreciate fuel injection because of how it used to be, even though most of us didn't have to deal with maybe the way it used to be. When I first started driving, it was in the middle ground where you had to step on the, well, sometimes you didn't have to, but it certainly helped to step on the gas once, and that allowed some fuel to flow through. So then you can turn the car on and it would fire. Not that there maybe wasn't still enough left since the last time you drove where you could still get the explosion, but sometimes you get the, and then it would turn over. But there was nothing that was automatically spraying extra fuel into the combustion chamber for an explosion to occur. Okay, other questions on this? Which part? Oh, I did warn you before. That is very hard to talk about the this keyword without saying this a zillion times. I guess that is an advantage in some other languages like Python. Instead of this, they use the word self. And even though I prefer the word this, because I guess I've just been using it longer, self probably is easier to talk about, because I think it's a word that we don't use as often. Like we use the word this all the time. it's maybe becomes a little problematic. Okay. So now that you've seen what's called a reasonable answer, we hopefully see that this really wasn't bad. But there's enough new stuff that we're trying to juggle here that, you know, this isn't, none of these individual lines are overly complex, right? But it's a matter of getting each of them put together in the right order and ultimately giving yourself the answer. So one statement I usually make is something along the lines of all hard programs are made up of a bunch of easy parts. If I showed you the source code of Microsoft Windows 11, you're going to see plenty of stuff that you recognize. It's going to be for loops. It's going to be int this equals this and all sorts of stuff like that. You're going to see pointer stuff because it's written in C++. So these things are going to be very familiar to you. You could look at the source code of Microsoft Windows right now and understand it on a line-by-line basis, maybe even on a relatively small function basis. But then you realize that there's, you know, 6,000 classes and, you know, 3.5 million lines of code or something like that. And all of a sudden it gets a little overwhelming, even though each of those 3.5 million lines of code you would understand, or a lot of them. All right, so as we have it standing right now, and actually I want to give myself, I'm going to change my fraction to 1/4. So we have 6/8 is our answer there, right? So I chose that because now we have a fraction we look at and says, well, maybe I want to reduce that. Okay. So 6/8 is the correct answer. Nothing wrong with that. and it's just as good mathematically as its reduced version. But we might say, hey, I want to reduce this number. What does it mean to reduce a fraction? Go ahead. Okay, well, okay. So then what does it mean to simplify it? What's the process? What do we have to do? Okay. Okay, well, why did you stop at 2? Why didn't you go higher than that? What is 2? When you said they're both divisible by 2, why did you choose 2? Yeah, I've never thought about that. And that's the problem why programming is hard. We're so good at solving problems, we don't think, we have trouble articulating how we solve them. Okay, well, but they're also divisible by 1, aren't they? Ah, you had to find the value, the greatest value that evenly divided the numerator and the denominator. That's the dude you want. Once you find the greatest value that evenly divides both of them, then you can reduce them by dividing each one by that value. That makes sense? So let's go in here. And why don't we go ahead? Why don't we add an additional ability? That way we get our full-fledged fraction, and then if we want, we can point at that fraction and say, "Reduce yourself," and then he'll reduce himself, and that'll allow us to kind of show this idea of changing values internally versus returning a value. All right. So we're going to have a function here that returns nothing. When I tell a fraction to reduce itself, I'm not asking him to return to me a new fraction that is his reduced form. I'm asking him to actually internally modify himself to be his reduced form. I mean, it's a choice I'm making. Nothing would say I couldn't write a function called reduce that didn't change the original fraction and just handed you a copy of it that's reduced. But in this case, I'm purposely saying, I'm just going to be able to ask an individual fraction to reduce himself, and he'll just, change himself to be in the simplest terms, simplifying that fraction. This guy will be called reduce. He does not need any inputs because he already knows his numerator and his denominator through this keyword. So we'll go and implement this guy. All right. So what we're looking for is we are looking for the greatest value that evenly divides both the numerator and the denominator. Now, the largest value that even has a possible chance of evenly dividing both of them is the smaller of the two, numerator and denominator, right? If I'm looking at a 6/8, even though as a human being, we can glance at that and say a 6 isn't going to divide an 8. But if we just think about it generically, we know that an 8 would never possibly divide a value that's smaller than it. Possibly a smaller value could evenly divide a value that's bigger than this. In this example, that's not the case. But if I had 6/12, for example, it would be the case, right? So we're going to start off by saying, let's figure out what the maximum possible value is that evenly divides both of them and operate off of that. So we're going to start off with the maximum or the minimum value of our numerator and denominator. So I'm going to say int min. And I'm just going to go ahead and pick one of them. So I'll say this numerator. So I'm going to say that the numerator is the minimum value. But then I'm going to ask a question. If this denominator is less than min, then update min to be equal to this denominator. What do you mean the new denominator? I'm just setting min equal to whatever the smallest of the two numbers are. This is numerator. This is denominator. I'm just making a guess on this line saying Let's just assume the smaller of the two values is numerator. Then I'm going to check my work. Well, is the denominator actually smaller? If it was, change min to be equal to the denominator. All right, so now I have stored inside of min the largest value that might evenly divide both the numerator and the denominator. In this case, we know that won't be the case. Right now, in my example right here, min is equal to 6. I started it off being equal to 6. Then I made sure that 8 was not less than 6. Is 8 less than 6? It's not. So I did not change it. So min is equal to 6, its original value, which was the numerator. Okay. So we'll say min currently holds the largest possible value that might evenly divide Newman. All right, so now what we need to do is we need to loop, go on a voyage, counting down from, now do we have a number that we know for a fact will evenly divide the numerator and the denominator? Well, 1. Regardless of what the numerator and denominator is, won't 1 always evenly divide it? Yep. So we know we'll have a stopping case. We know we're, because math says that we'll eventually run into a number that evenly divides both of them. It might be 1. And if it's 1, that means it's already reduced, right? Okay, but it might be 1. So we're going to create a loop for int I is equal to 1. I'm sorry, is equal to min. I is greater than or equal to 1. I minus minus. So we'll start off at the largest value that might evenly divide both of them. And we'll start counting down all the way to 1, knowing that if I get to 1, I'm going to exit this. Well, when I exit this loop, I know I've done everything I could. All right. So each time through, we're going to ask the question, if this numerator mod I is equivalent to 0. And so if my numerator is evenly divisible by I and my denominator is evenly divisible by I. That's what this question asks, right? If my numerator is evenly divisible by I, as well as my denominator is evenly divisible by I now have my greatest common divisor. So how do I reduce my fraction? I divide both my numerator and my denominator by I. This numerator is equal to this numerator divided by I. This denominator is equal to this denominator divided by I. Now I've reduced this fraction, right? And I can go ahead and return. It's a void function, so I'm not returning a value, but remember the return keyword makes a function immediately end. I've done my work, right? I found the greatest value that even divides both the numerator and the denominator. So I'll go ahead and update this guy's numerator to be whatever it currently is divided by I. I'll update this guy's denominator to be whatever it currently is divided by I. And then I'll kill off this method. I've done my job.
So percentage, that's dividing both.
Remainder, yep. And where you've seen this before is when we were checking to see if things were even or odd, right? You know, something mod 2 equals 0. If that's true, it's an even number. If it's false, it's an odd number. Now we're just saying, is this guy evenly divisible by this guy? That is, when I take this guy, and to your point, and I divide it by this guy, it has a remainder of 0. That means it went into it an even number of times. So we found something that evenly divides it. And if I found something that evenly divides both the numerator and the denominator, and I happen to count down from the largest possible value towards the smallest possible value, then I'll go ahead and do this. I know that I will eventually get into this if statement because I'll eventually hit a 1, correct? And if I hit a 1, I'll divide the numerator by 1, doesn't do anything. I'll divide the denominator by 1, which doesn't change it. So I could make the argument, why would I ever waste my time with a 1? So I could just say greater than 1 there. Never actually check the 1, because if I'm still alive, if I haven't killed off this function, by the time I hit 2, I'm not changing my numerator and denominator. My fraction was already reduced. It was already in its simplest form. Make sense? All right, so that's what reduce does. So now we can come back out here to main. I tell F3 to display itself, and then I tell him to reduce himself. And then I tell him to display himself again. We'll see that we get the reduced version of him, 3/4. All right, make sense what we're doing there? Our real goal here is always break things down to their simplest steps. What did I do first? I figured out what is the largest value that might evenly divide both of them. Step 1. Step 2, let's try every value from that guy down to 1, or down to 2 in this case, and test each key in the lock. Does this guy evenly divide both of them? If no, let's try the next guy. Does this guy evenly divide both of them? If no, keep going until I finally run out of things to test. And then I fall out of this for loop and said, look, I tried everything, nothing evenly divided them. I know 1 will, but that's not going to change them. So just let this method finish and die a natural death. And I just won't change anything. Go ahead.
What is the double column?
This, well, so I think for our, this is a scoping rule. I think for our intents and purposes here, the double colon will always follow the name of the class that you're implementing. And what it does is it links this reduce to this prototype for reduce. It connects those two guys together.
And that would never be in the main.
No, because what it's doing is allowing us to do this instead of it's letting me do that instead of actually putting my implementation right there. That's what it's allowing me to do. It's saying, allow me to prototype it here and then implement it later on. But the way I let the header file know that I'm actually implementing it is with this kind of almost like raising a flag. Hey, I belong to you. Don't forget about me. And it's really a directive to the compiler to make sure it goes through and catches it. All right. All right, so questions about that? All right, so now to show a problem. Let's start off. I'm going to go back and get our random number code with our seed value and then our random number, things that allow us to get big. What I want to do is I want to get a really big numerator, a really big denominator. So we need standard lib and time.h. It's just quicker for me to go and steal these. And then I will steal those two. Well, steal this one. That starts it off. That seeds my value, so we get different random numbers. And then my actual value is just this rand function. I think rand gives me a number in the range of all. I'll just do this for now. Let me back up just for a second. I'm gonna have to give you a link to this anyways. I was gonna say so I can post the code up on Slack, but if I share it right now, and then I make a change, it's gonna have changed. Yeah. Yeah, I mean, because this link's gonna always be the same link. WB1RZ, isn't that one, right? Oh, it's giving me different links. I guess we could try it. I don't know if it gives you a snapshot of the current code. Okay, well, that would be pretty handy. Current code to solve initial fraction and reduce problem with that. All right, and now I'm gonna go start making changes to it. So we'll see if it that takes. All right, so I'll go grab my my srand again. That seeds the random number generator. And then I'll go ahead and give myself a random numerator and a random denominator. And hopefully these guys are sufficiently scary. I actually think that, well, I think we did see it. It'll only do positives. The range of all integers, positive numbers, but I'm not 100% positive. You got negative numbers? Okay, so possibly it'll give you negative numbers, I guess. We could force it to be well, you could. That would just be a negative fraction. That would be equivalent to that fraction being times -1. But we can certainly give ourselves here, we'll just write a int get positive random. I'll prototype it up top. I'll write it down here. And this guy will say int num is equal to rand if num less than 0, num is equal to num times -1, return num. So now we'll always get positive numbers. All right, so we're going to say these are big fractions, right? You noticed the delay, didn't you?
Yeah.
So now we have programs that they're not running instantaneously. And can you imagine if you started writing a collection let's say you had a whole bunch of fractions that we, were these giant fractions, and we added them all up, and now you have a humongous fraction. But you summed every single one of them and reduced them along the way. That might take a really, really, really long time, right? Like days, months, years. Reducing fractions, as simple as it seems like it might be, because we think about adding fractions and reducing fractions as not being like hard math, right? But it actually is a time complexity issue, where the more you're doing it and the larger numbers you're dealing with, I mean, you might be dealing with numbers in the billions, right? Or trillions or quadrillions. We let the sum go up to like long values, which we'll do here in a second. So then what you end up with is you end up with having a ridiculously huge fraction that would take, for all intents and purposes, longer than we're willing to wait to reduce. So let's mimic this. I'm just going to change our numerator and our denominator to longs. Okay. And actually, if I really wanted to, I can make it an unsigned long, which would then take away its ability to hold negative numbers. So I would get the full 2 to the 64th power value. So this is 2 to the 64th. That's the largest value that we can hold inside of a long. Big old number. Okay. And remember, the way we're currently reducing is to do what? Taking the numerator and denominator, take this huge number and this huge number, find out the smaller of those two huge numbers, and then start counting down towards 1. I don't care how fast your computer is, if you have to count down 1 trillion or 50 trillion numbers, it's going to take some time. Okay, so let's see it in action. So I'll go ahead and update these guys to be longs. The only reason I'm making this change is so that our fractions are now capable of holding bigger values, to really force this example. So anytime I have an int, I'll change it to a long right now. Common denominator is going to be a long. Okay. And a long is just a 64-bit integer instead of a 32-bit integer. Hold bigger values. No, because an int is a long. It's just a subset of it. So even though this is returning an int, when I pass an int here, it'll cast it to a long. But now what I'm allowing myself to do here is now add a whole bunch of them together. Okay. So we still see this guy has a delay, right? It's taking some time. So now what I want to do is I want to go through and maybe add 100 random fractions together. 100, that's not that big of a value, right? We'll call the answer like that. We'll do something 100 times. What will we do 100 times? We're going to set F1 equal to that, F2 equal to that. We'll set answer equal to F1 add F2. Then we'll say answer, reduce yourself. And finally, when all is said and done, we'll tell answer to display himself. So I just gave myself some variables to hold values here whose scope is accessible after that for loop. I'm going to go through, I'm going to do something 100 times. What am I going to do? I'll generate a new giant fraction. I'll generate another new giant fraction. I'll then add those two fractions together, giving myself an answer, and then I'll reduce that fraction. Okay. Now what I'm going to do is I want that guy to be, in fact, I'm going to have it be on my running total here. So I'm going to start F1 off before this. And I'll go ahead and get a F2. I'll get my answer. I'll reduce my answer. Then I'm going to set, I'll be a good steward here. So I'll clean up the old memory associated with F1. I'm done using that fraction because I just used him here to do some adding, but I got a brand new memory address, new memory. That's the answer. I reduced it. Then I'll get rid of the old memory associated with F1. And I'll set F1 equal to answer. So what am I doing here is 100 times I'm creating a running total. First time through, F1 plus F2 is answer. The next time that I'm setting F1 equal to my new answer. So then it's going to be answer plus F2, answer plus a new F2, answer plus a new F2, over and over and over again, 100 times. So in the end here, what should answer be equal to? It should be equal to the sum of 100 potentially giant fractions. Oh, doesn't like me putting them all in one line. Not declared in that scope. Oh, I'm missing a semicolon here. There we go. It's only doing it 100 times. Now we saw how long it took to reduce a single fraction that was a random integer between 0 and 2.1 billion. So it possibly had to go through 2.1 billion times, right? And we saw in our couple of examples, it took what? Two seconds. But now every single time we add, our possible answer is 4.2 billion, 8.4 billion, so on and so forth. Doesn't take very long until we're working with humongous numbers, where even for 100 numbers like this, probably it might still be running by next class. Not kidding. So this would be an example of a time complexity problem that we would say this is unacceptable, right? Fractions aren't that hard. Why did I have such a hard time doing this? Now we can look at putting some shortcuts in. You know, there's some like math shortcuts you can go in for our reduced fractions that, you know, really the biggest the number might be that we actually have to test is the square root of our minimum number, something like that. So fine, you're reducing the number of values you're checking, but it's still a humongous number of values. Okay, so there's a, this is a known time complexity problem, greatest common divisor. a known time complexity problem that has some solutions. Most famous is the Euclidean algorithm. So the Euclidean algorithm attempts to find the greatest common divisor of two numbers. Effectively what we're looking for, right? See, this guy's still cooking. We'll let him keep cooking. So we can see if we can fix it before it finishes. We will be able to. So we'll look up the Euclidean algorithm. This guy will have some pseudocode in first. It's short. It's not a long algorithm. So this is effectively the algorithm. We'll update it to be C++ code. So we'll go into our Fractionhpp. Now, the greatest common divisor algorithm that we're going to use, we don't want them to be able to use it externally. You don't need it, but it's something we're going to want to leverage inside of our program, right? Because clearly our current version of reduce is not going to cut it, right? So I'm going to actually put this, I need to stop it. Okay, we can all agree we're not happy with the performance of the current program. So we'll go ahead and stop that guy. So inside the private section here, I'm going to add another function, just like my other functions, but I'm actually putting this one in the private section because I'm only going to use it internally in my fraction class. All right, so it's going to return a long, and I'm just going to call it GCD. And it's going to take a long A and a long B as a parameter. I'll actually copy this. I'll go copy the other thing again in a second. I'll put this down here right before reduce. Okay. So this guy takes in an A and B, and what greatest common divisor does is it returns the largest value that evenly divides both A and B. That's what it does. So it says, as long as B is not equal to 0, we're going to do something. While B is not equal to 0, do some stuff. What stuff am I going to do? Well, I'm going to set a variable t equal to the current value of B. So I'll define t before this, long t. T is equal to current value of B. Then we'll set B equal to A mod B. A divided by the remainder of A divided by B. B is equal to A mod B. Preserve the value of B and T. Update B to be A mod B. And then set A to the current value of T. When all is said and done, as soon as we've whittled B down to 0, I can return the current value of A. Return A. Now, we don't have to know how this works or why this works, just that it works. Okay. Some smart mathematician guy, Euclid, came up with his algorithm that finds the largest value that evenly divides two numbers. So now, instead of all of this crap that I have inside of reduce, I'll just say long. Just call this guy div. That was it. taken word. That's why it was in red. This guy will be equal to this GCD, and I'll pass it this numerator. And this is denominator. So I'm passing it the two longs that I want to find the greatest common value that divides both of them. I'll call GCD on that guy, and he'll spit out the divisor. And then I'll say this numerator is equal to this numerator divided by divisor. This denominator is equal to this denominator divided by divisor. And then I'm done. Go back out the main, run this. Already done. And clearly that's the right answer. It's the right answer, trust me. Okay. But you're seeing the difference. We would look at this and say, well, there's nothing overly special about what we wrote there other than we don't know why it works, right? There's mathy stuff behind the scenes. You can go look at the Wikipedia and it tells you the math behind it, but this is not overly amazing other than it's like 7 lines of stuff. But you see the power of the problem it just solved. Code that would have taken forever to finish, and I mean days, to now it instantly finishes. Pretty interesting, huh? All right, questions about any of this stuff? All right, I'll give you a break over the weekend, no homework. We'll come back on Tuesday and we'll talk about some new stuff. I won't give you homework over Thanksgiving, but I promise I'll give you a doozy afterwards. Okay, so between now and then, really try to practice some of these things. Give yourself some drill problems to work on. So don't just give up on coding, but I'll give you a little breather. I'll post it right now. And hold on, truth in advertising, did I not tell you that the first week of class? And then you're going to get to the point where you'll look at that and say, I cannot believe I spent 6 hours on that.
Oh yeah, no, the problem is we spent like 6 hours. Well, you spent like 3 hours, and you came up an hour, and you're like, okay, we can't do this on either. I think it's really going to do like 6 point progression, and I just realized my code doesn't do it. So, and then we went through the whole thing, and then I realized that after 2 hours, the problem I was staring at is that I had the confusion of where you're supposed to name it, how you name the answer. I just couldn't write a name. Like, oh, I'm just gonna name it friend.
But I did mention friend in class.
I'm like, wait a minute. I'm like, why isn't this working? Because Aiden had like the same code. I matched it.